Right, I am giving this on behalf of Matthew Turner, a software engineer at a stealth startup, which has now included its name on the slides, called Tetrate. Prior to that, he was a Kubernetes consultant and did DevOps at Skyscanner, and then Cisco originally, where he states he did not work on networks, probably to avoid flames. And prior to that, Redgate. He's done a lot of stuff here, I won't continue, but lots of things there, embedded C included. And this talk is looking at how Istio transfers packets. I suppose the pertinent question is, how many people here have used Istio in some way? Cool, kicking the tires. How many people here are confident they know what Istio is supposed to be? Yeah, that's probably a trick question. It's all things to all men at this point in time. There was a question from the product manager, Dan Cerulli, at KubeCon Seattle, as to whether they'd launched too much. I think because they launched so much and cornered so much of the market with that, it was the right thing to do. But as you've seen, the adoption time for Istio, the lead time on development is very long because of the number of challenges and number of implementation, infrastructure targets. So, yeah, most importantly, useful as a mental model. Yeah, okay, so an understanding of what Istio is and does, the service mesh will become slightly more apparent. So, this is the diagram that is in every Istio talk ever, and basically a standard diagram. We're calling those grey boxes pods, and this would replace something traditionally like Hystrix for a distributed system service library. So instead of baking our application code that manages rate limiting, circuit breaking, negotiation with other services, instead of baking that as a JVM library, a library in our JVM application, we externalize it. We put it in something called Envoy, which is a proxy written in C++ with devastating performance, it appears. And because a Kubernetes pod is a shared network namespace, then we can force all traffic into Envoy. This means that we've got a centralized place of control for the whole mesh, and it gives us a place to coordinate everything. So, the first question when we're looking at how a packet works is ingress. Packet is Nyanket today. Now, a packet can start its journey through the famous diagram. It's hitting one pod of potentially service A, to one instance of that pod. What is that pod? In Istio, it hits Envoy. So there's one IP, and for that IP, the traffic is all routed to the Envoy process inside it, for every port that it hits by default. This is called the sidecar model, so putting multiple containers into one pod, and of course a pod can have more than one container. Istio must have this Envoy sidecar service container in order to join the mesh. Otherwise, there is no way it can talk to other services, because Envoy does all the traffic negotiation. So, what happens when it hits a pod IP? What's that blue box? So, this is a representation of the namespace model. Now, it must be noted they're not nested like this, but it's a nice way to imagine it. And of course, you can turn things on and off. So, the user namespace, as you mentioned, is not actually enabled in Kubernetes or Docker by default at all. Can be enabled, but it breaks a load of things. We also have C groups that are not on here, which are essentially hardware namespaces and arguably misnamed. So a pod is essentially a collection of containers stuck together. You can see the namespaces they share, but they have their own interprocess, their own essentially localization, like host name, and the mount namespace, which is the contents of the file system that they sit on. And so here you can see a relatively standard idea for a pod where you just have Nginx and then another container with a separate responsibility running alongside it. It may seem like a lot of resource utilization. When you think about that logger running from scratch and just having a process inside it, it's actually not very much, and you end up with a very granular, addressable resource to hang security policies on. This is called the atomic unit of deployment because you can't deploy anything less than a pod, and you can't split them up. So, the network namespace contains interfaces, standard interfaces, but virtualized. Also IPs, ports, socket, route tables, and IP tables rules. It is a whole network namespace that you'd imagine from the host, but just placed within this frame of reality, this window that the container gives to everything inside it. And then applications inside it believe that they are, for example, all locally on this a different subnet to where the packet actually ends up entering the physical network. That's because we've nested these other subnets next to each other, sometimes inside each other. This is just networking, but hidden behind this abstraction. But there is only one IP publicly, so that ETH0 that breaks out and bridges the container network with the host network only ever has one IP. Let's say Nginx binds to port 8080 here. We can have another container in the same pod that shares the same IP and the same IP table space and the same local host loopback adapter, so it can't bind to 8080. There's only one port. Complexities aside, essentially it's that they're sharing the same network adapter. If we replace FluentD with something more exciting, for example, Envoy in the proxy, we can then set up IP tables rules to intercept all traffic in or out of the pod and forward it straight to Envoy. This is the magic of the service mesh. This is how the whole thing bootstraps. This is called the sidecar model. There are other ways to do this. Linkerd kind of pioneered this whole thing, but they did not run sidecars like this because the Linkerd process is 100 megs, it's JVM, it's Scala, so not very committable, not very friendly for people to contribute patches to, also really heavyweight, so you would run a single instance and then you have to ask questions of security isolation. So let's see how this happens and look at how a pod is set up. First, the pod is built by the container runtime engine. Namespace and C groups are configured. There is some persistence, maybe mount namespace are inside, maybe volumes that are mounted in. And of course, it's just a running Linux system. Because it's a running Linux system, if we set up an IP tables rule out there in the network namespace, and our container in here starts and restarts a few times, it will go back into exactly the same network namespace as it started off. That's done magically under the hood with a pause container, but to all intents and purposes, those IP tables rules are persistent for the lifetime of the pod. So, I have two Kubernetes init containers. First, it's just Alpine, which runs a command, turns on core dump. And here we're setting up IP tables to do the interception. So this is all in the local NAT table. And this is a container that Istio actually runs. The proxy init container is a load of bash, I'm happy to say, that runs a load of IP tables. Just like everything else in container networking, it's all IP tables all the way down. And so what we have here is a proxy init container that is performing privileged operations on the network namespace. So that means it needs cat net admin to do that, which fortunately, because it's an init container, runs before the application and then folds down on itself and closes, and the capability dies with the pod. So we can do this safely. There is Envoy is then listening on 15,001, and a new IP tables chain called Istio redirect is configured. Some more detail deeply. Okay, so at this point we have IP tables configured for all networking to go to Envoy. We have Envoy listening on a port, so the IP tables rules can fire all the packets to that port on the loopback adapter. And we'll start the containers. The app and the sidecar Istio proxy image, which contains Envoy, it listens on 15,001 and hilariously runs as UID 1337. Okay. That covered how the traffic gets to and from an app in a pod, but taking a step back, we're actually talking about the whole caboodle. What happens when service A wants to talk to service B? First, we have service discovery. This is not your standard Kubernetes service discovery. You'll be horrified to know. Envoy provides its own service discovery using the virtual service abstraction. This means that you have to address services on the mesh. That's done with secure naming and various other things that I'm happy to talk about afterwards, but are a little bit deep. And essentially you can think of this as a layer 7 overlay network. Although the notes tell me it's more like an out-of-process layer 7 services library. Addressing connections, etc. is still done at layer 3 and 4, and actually mostly at layer 3. So every IP and port combination is turned into just an IP by Envoy, and that is part of its internal optimizations for traffic routing, apparently. So, excuse me. Yeah, so essentially what we're doing here with service discovery is just putting in a DNS name, which actually, in Istio terms, ends up being the SAN in a TLS certificate, and that is resolved to an IP, which is load balanced across multiple instances of the service, and Envoy decides where that packet then goes. Just a quick aside as to how that integration with Kubernetes works. It uses an little known feature, which is endpoints, I presume. I'll skip over this, sorry, it's going. So, we can query a service via the REST API, resolving back to the cluster. kubedns exposes it over DLS, but what we get here is the cluster IP, which is what makes the system work. That's what Istio ultimately addresses, but not the way that Envoy addresses it in the first place. We have some pods and IPs. These are all queryable just through kubectl API. Here we are. So the endpoints are the interesting things here that we care about. This is the container network interface address for the various pods. These are the IPs that Envoy is ultimately routing to. And if we open this up, there's everything that we might want to know about an endpoint for a service. Envoy is sitting in the data path, so it can intercept these requests and send them to whichever endpoint it wants to. It can empirically see what latencies each instance is giving and pick the quickest one. And this is kind of counterintuitive because an upsell of Istio is it's faster. To put a proxy in the request path is faster than just plain HTTP 1.1. Why would that be? Two reasons. First of all, we can do this latency-aware load balancing because Envoy has a visibility of everything in the mesh. And secondarily, everything is a persistent HTTP2 connection. So that is a lack of renegotiation, everything's already open, you don't have to SYNAC every time you start something. Now your mileage will totally vary, and I won't stand by that at all, but that's the theoretical upsell. Yeah, so, building up the view, Pilot is the first control plane component that we're looking at here. This is how we write to Envoy. Envoy has an API-driven configuration model, and it's also got a super neat internal configuration model, which is essentially immutable. So I've got a request come in to Envoy. It attaches a pointer to its configuration to the request, and as it handles it, it knows what its configuration is. Then an API call comes into that Envoy instance and changes its configuration. It duplicates its config, and new requests get a pointer to that new config. That means that not only can it do crazy hot reloading stuff, but also you can drain a connection over days if you really want to, because you can keep as many copies, as far as memory bounds you, of your configuration as you need. Super nifty feature, basically means you get zero downtime, reconfigurations and restarts. So, Istio can get all that it needs from service discovery from its control plane API. Pilot is writing to these Envoy APIs all the time, and it also supports a bunch of other systems. There's a huge amount of functionality afforded this way. So we can route from outside the cluster, we can duplicate traffic, we can route traffic based on layer 7 properties, because the TLS bundling and unbundling is also done by Envoy. It's plain text to the application. they're in the same namespace, that's a reasonable security boundary. And that means that you can route based on arbitrary values, maybe a cookie, of course the DNS name because it's there, but in the SAN, but anything that is exposed by the application. Canary deployments is another form of traffic shifting because you can do this across the whole cluster. Circuit breaking, preventing cascading failures by breaking the circuit early and stopping requests to a service that's underperforming. And fault injection, so you can test your circuit breakers and your latency responses. So we found service B, can the packet proceed? Again, it hits Envoy. Pilot has configured it with the relevant configuration. So Envoy knows whether or not to accept the packet from the previous Envoy, giving us some protection against compromised meshes. And there's also rate limiting. So this policy check going back to Mixer says, well, across all the instances of this service, how many times has this been hit? And is that within a reasonable bound? If it's not, then we are just going to cut the connection there and prevent Envoy from responding to that packet. So although Mixer is shown as part of the control plane, I would say it is slow path for the data plane. It's quite the slide, isn't it? There's all sorts of other things involved here, of course. We have RBAC on the Mixer, which is layer 7 RBAC. So that is the host we're hitting, the path, and the request verb, HTTP key verbiage we're using, with rate limiting functionality. And we can also export metrics to Prometheus or Elasticsearch. This is all entirely pluggable. There is also the ability to attach traces to these things if we pass request context through the chain of a set of microservices requests. We also get free tracing from these. Yep, ACLs, auth, and the tracing there as well. The Fraulein wants to know what's happening with the packets. Is this allowed? Do we know where we're going? This lady is called Eve. So we stick this packet in a TLS tunnel. We negotiate the connection. We do another set of authentication here at layer 7. So not only do we care about the origin of the packet, we also care about the layer 7 wrapper and whether or not those two envoys can mutually authenticate with a shared trusted root store. And that is what Citadel provides, which is the certificate authority. It's pluggable into Vault at this stage, which then means you can plug it into a KMS or an HSM or a physical device. Cloud HSM or an actual HSM. So, at this point, we have managed to get a packet from one envoy to the other. Now, as you can imagine, debugging this is not a particularly friendly state of affairs, but the balance then becomes whether we want to re-implement these things ourselves, and if we have a hard requirement for TLS or running our own PKI, I'd say this immediately becomes a compelling prospect. There's a couple of boxes missing from the diagram, of course. There's a kubectl out on one side, we've got the API server and etcd. All these things are exposed as custom resource definitions, or CRDs, in Kubernetes, and as such, it's just an extension of the Kubernetes API in some ways. Equally to ingress, there is also egress control. This does support layer 7 load balancing because Istio embraces that. When I say load balancing, I mean egress policy. Yeah. It is, as all these things, is configurable and opt-in, but it does mean that you can provide some sort of useful layer 7 interception that's not just Squid. So, I hope that conveyed the traversal of a packet, how we call the control plane, and gives some more information on Istio. Thank you very much from Matt and me.